Hey everyone, welcome back to another video. So today's day 5 of Algorithmas. Today we're going to be doing this algorithm here, which is to count how many jumps it takes for a frog to cross from one point to another point. So if you have a look, we can see that a small frog wants to get to the other side of the road. The frog is currently located at position X, so 10, and wants to get to a position greater to or equal to Y, which is 85. And it can always jump a fixed distance, which is D. So if you imagine it starts at 10, if it jumps 30, it is now at 40, so that is one jump. If it jumps again, it is now at 70, which is two jumps, and that's not enough to reach 85. So if it jumps again, that will put it at 100, which allows it to be greater than 85, because remember, we have to either reach 85 or exceed it, and that is essentially how many jumps it takes the frog to go from A to B, or in this case from X to Y. So let's give it a try. I'm going to be using C# for the language as usual. I can do this in other languages, but again, I'm just used to using C#. If you use Python, Ruby, JavaScript, whatever, then it doesn't really matter which language you use for this. It's fairly straightforward. So I'm just gonna change this, and you can see I'm using the inbuilt ID, which again doesn't have IntelliSense, so I can't automatically complete things and get those little autocomplete pop-ups for methods and things. So it is going to be a little bit annoying, but yeah. So same concept. So we're going to have X, Y, and D is the number of jumps. So I think what I want to do is just give these names that I can remember. So var jumps equals D, and I will say, let's see, var initial position pos equals X, and var target pos or position equals Y. So now we've got names that make sense. Now there's two ways you can do this. One way is to calculate the difference between these two and essentially keep adding the distance that's in jumps to your initial distance until you surpass Y. And you would do that by using, say, a while loop that just checks to see if you surpassed Y or not. That's a very, very simple way, but the space-time complexity of that is quite high. While loops take are quite performance heavy, so they take longer to execute. So there is another alternative way to do this, a very, very simple way. So we know that the difference between the initial and the target position is the total distance that we need to go. So I'm going to create a new variable called total distance, and it's going to be equal to Y minus X. So let's say Y was 85, X was 10, so the total distance we need to travel is 75. And we know that each jump is equivalent to 30. So let's just change that 75 to, say, 90, for example. Let's imagine this total distance was 90. So if each jump is 30, then if we just did 90 divided by 30, we would get 3, which is the total number of jumps. Nice and simple, but obviously we're not going to be working with nice round numbers all the time. So what we could do is, firstly, if the total distance, and then if modulo, which is basically a way to divide, and just what it does is it returns to you the remainder. So if there is no remainder, that means it's perfectly divisible. So let's just check firstly if it's perfectly divisible. And we're going to do jumps. And if it is perfectly divisible, then we don't expect any remainder. So we would expect the final output to be 0 for total distance modulo jumps. And if that is true, we know it is a perfectly divisible number, total distance by jumps. Then what we can do is just return, we're returning an integer, that's fine. So return total distance divided by jumps. Nice and easy. But what if this total distance modulo jumps is not equal to 0? If that's the case, then what we can do is can just do else and then return total distance divided by jumps and +1. Now the reason we're going to do +1 is, let's say in our example we have 75 as the total distance, each jump is 30. 30, if you divide that into 75, is going to be, let's see, about 1. I think that's 1.25, 1.5. No, sorry, 2.5. I think that's 2.5, yeah. Or 2. So it's 2 point something. But what happens is when it's compiled, it's gonna return the single integer that it is rounded down to. So it's gonna return 2, and that's not what we want. We would want 3 because it's gonna take 3 jumps to surpass it, which is why we always add 1. The number isn't perfectly divisible. So what we're going to do is we've got our statement there, which is all fine. So we're going to give this a test run. Okay, so we failed. This normally happens, don't worry. Why is it failing? It is because we're using the wrong brackets. That's not a problem. We'll just change these for curly brackets, common mistake. And we run it again. And you can see we've successfully passed the first set of tests, so that's all fine. We've passed this input, so what we're going to do is we're going to submit our task and we're going to see what we get. And so what's going to happen is we're going to calculate our kind of total efficiency. Okay, so you can see that's 100. Now, if you had done this with the while loop, you wouldn't have gotten 100, you would have gotten less than that. That's because using a while loop is a lot more performance heavy. So if you have a look here, if we go down to one of these, you can see that space-time complexity is not that high. You can see up here it's 0.1, and it didn't take very long to execute. If this was a while loop, it would have taken a lot longer. Not a lot longer, like milliseconds longer, but it would have just taken overall longer time. And this does scale up, the more operations you have in your application. So that was the, I guess we call it the frog jump algorithm. It's quite straightforward, not too difficult. You can solve this with a while loop if you wanted. But yeah, there you go, guys. So we'll see you next time for day 6, where we're going to be doing a little bit more of a difficult algorithm. We're going to step these up in difficulty each time. So thanks for watching, guys, and I'll see you next time. See ya.